So when is a thin wall thick? When is a thick wall thin? Well, fortunately, ASME have provided us a definition which helps us to determine this. So the two expressions on the screen, the first is given in terms of the inside radius and the wall thickness. The second given in terms of the outside diameter and the inside diameter. They're mathematically equivalent. And essentially, what we're saying is if the inside radius or the thickness is less than or equal to 4, then it's a thick wall. Equally, if the outside diameter or the inside diameter is greater than or equal to 1.25, then it's a thick wall. So to give some context to these ratios, I've drawn out a thin wall cross-section on the left, a thick wall cross-section on the right, and then a wall section at the transition point in the middle. Now, wall thickness in itself doesn't determine that it has to be assessed in any particular way. So to understand that, we need to look at some specific stress considerations for thick wall structures operating in high pressure environments, which may otherwise be unimportant for thin wall structures in low pressure environments. Okay, so firstly, internal bore yielding, also known as autofrettage, can occur. So with the high pressures, we get high radial and hoop stresses, which are developed at the internal diameter of the structure. And this can give rise to stresses in excess of the elastic yield limit and can result in regions of plasticity. So for the example of the image on the right, this is represented by a material coloured in red. So for ductile materials, this can be allowed to extend some way into the wall thickness without compromising the overall integrity of the structure. Moreover, autofrettage can be introduced by design, as the residual compression that's left on that inside surface can be beneficial in terms of retarding crack growth. So it's just something that is specific to thick walls that we never really had prior to this. We also need to be aware that these high internal stresses are concentrated further at sharp corners, such as bore intersections and seal pockets. These are likely crack initiation sites for cyclic failure modes such as fatigue. And thirdly, the transition from thin to thick wall also has a tendency to change the likely fatigue failure mode from leak before burst to fast fracture. So what do I mean by that? Well, as a crack propagates, assuming it starts at the inside surface, as it propagates through the wall thickness of the structure, it grows in both the radial and circumferential directions. So for thin wall structures, it tends to reach the outer surface, having propagated only a small amount circumferentially, meaning that much of the cross-section is still intact and can contain the pressure. The crack reaching the OD results in a leak path, which can be detected, hence we call this leak before burst. And this gives us the opportunity to intervene prior to fracture. For thicker wall structures, the crack has much further to propagate radially, and as such propagates much further circumferentially too. So this can result in a crack reaching a critical size such that the remaining cross-section cannot contain the pressure and fast fracture occurs. So this obviously happens before any leak can be detected and any intervention can take place. A further consideration, which may be overlooked for thin wall vessels at lower temperatures, is that for thick wall structures, there is likely to be a non-uniform temperature profile through the component, resulting in differential thermal expansion and potentially significant thermal stresses. This may also exist due to differential thermal expansion rates if more than one material is present. Although this is not unique to high temperature applications, the increased change in temperature makes this effect more pronounced